This section is on solids of revolution. We're going to look at two types, the disks and the washers. We're not going to cover shells in this particular lecture. So the idea for disks and washers is that you have a representative rectangle representing part of your area you're going to revolve, and it is always perpendicular to your axis of rotation, always perpendicular. The shells are parallel, disks and washers perpendicular, and we revolve this rectangle, and when we do this we get a disk. And what we'll be doing is just adding up a bunch of these infinitesimally thin disks to get a solid. So here's a locus of the whole piece. Now, an example, we're taking y equals rad x between these points A and B. We're rotating around the x-axis, and so imagine we're revolving one rectangle. And then the idea is that we would have a lot of these, and of course instead of having just 5, we would have an infinite number of infinitely thin ones. So if we just do more and more of these, we get a better and better fit. And of course the point is that we use an infinite number of infinitely thin rectangles, we get our perfect solid. So that's disks, because there's no space between the region being revolved and the axis of rotation. Now we come back over here, and if we reset this, let's get rid of the locus. Now if we move out to this distance, now what we have is some space between our region and our axis of rotation. So when you revolve, you get washers, which is basically a disk minus a disk. And so washers, one disk minus another disk, and we can see the same sort of thing down here. If we move our axis of rotation off of the x-axis in this case, and then we have this big hole in it. And here's, if you just move one of them around, then you can see that there is the hole in the middle of it. That's why we call it the washer method. So I'm going to go through several different examples of how we would do this. Okay, here we have the function y equals 4 minus x squared, and we're going to rotate it from 0 to 2. We're going to rotate it around the x-axis as x goes from 0 to 2. Now what happens is these are cylindrical disks, and so the volume of one cylinder is pi r squared times height. Again, volume equals pi r squared times height, and the height of the disk in this case, you can imagine it's on its end, is dx, and the radius is from the center, the axis of rotation, out to the end of the rectangle. So that's a distance of y. And so the way I think about it is we're going to rotate around a horizontal axis, so I now need a vertical rectangle. That will be a dx. X is going to go from 0 to 2, because I'm going to add up all these rectangles through the process of integration. I have my pi r squared still, so my pi I'll put out front because it's a constant multiple. And my radius is again from my axis of rotation up to the end of my rectangle, so that's y. So pi y squared dx, again it's squared because it's pi r squared. Then you can't integrate like this, you have to plug in 4 minus x squared for y. So here's your new integral. And in this chapter we don't spend so much time on solving the integrals as really setting them up. It comes out to 256 pi over 15. What you can do is in the calculator, you put this into function integrate, make it a fraction, and then of course you get 256 over 15, and you can just slap the pi on afterward. This is now a simple washer problem. We're going to take the space between y equals x squared and y equals x cubed and rotate it around the x-axis. And so you see there's all this open space between our area we're revolving and our axis. Again, with the horizontal axis, we have a vertical rectangle, and so it has a thickness of dx. And once again, the volume of this cylindrical disk is pi r squared times height. The height of the disk is horizontal. Imagine you've got this disk is sitting on its edge. So dx, x is going from 0 to 1 because these two functions intersect at 0, 0 and 1, 1. I have a pi out front. Now, for the washers, I have imagine I'm doing this washer minus this, or this disk minus this disk. So the outer disk has a radius of x squared, or f of x, so it's f of x squared. The inner disk has a height here, a radius of g of x, so that's g of x squared. So outer one minus the inner one. And so now what I can do is plug in x squared here, so x squared is x to the 4th, x cubed squared is x to the 6th, and now I can evaluate my integral fundamental theorem of calculus, plug in the limits, and I get an answer. This is a washer problem because what I'm doing is taking the yellow region defined by y equals 6 minus x, y equals 0, y equals 4, and x equals 0, the yellow region, and rotating around x equals 6. So the region touches at this point, but there's all this empty space here. Now I'm rotating around a vertical axis of rotation, and so I'll have a horizontal rectangle, which means I will have a thickness of dy. So I can put a dy here. Y is going to be going from 0 to 4. It doesn't go 0 to 6 or anything like that. The limits of integration are based upon the region that you are rotating. So that's 0 to 4, pi out front. My outer radius is from here to here, and that's always, as you go along the region, it's always from an x value of 6 to an x value of 0, so that's simply 6. So 6 squared, because remember the pi r squared, minus the inner radius. Well, from here to here is some random distance x. From an x value of 0 to some random place along our function is a distance x. The whole distance is 6, so if this is x and this is 6, then that means the intervening part, this part in between, is 6 minus x. So 6 minus x squared. And so then, to integrate this for x, we plug in 6 minus y, realizing that if this is y equals 6 minus x, we have to solve this equation for x to plug it in here. And then we have this big long integral with 6's all over the place. And that allows us to then go ahead and find the region that we would get if we rotate this. The next one we're going to look at is useful because it's the same region with all sorts of different rotations, as you'll see. So for this example here, we're taking the region defined by y equals 2x squared, this parabola, y equals 0 and x equals 2. So this sort of triangular type shape, and we're going to rotate around these 4 axes, the y-axis, the x-axis, y equals 8, x equals 2. So first the y-axis is over here. Well, there's all this empty space, so it's going to be washers. It's a vertical axis, so I need a horizontal rectangle, so that's a dy. I'll put my pi out front. Y is going from 0 to 8. I know it's going from 0 to 8 because this is x equals 2. 2 times 2 squared is 8, so this is a height of 8. Now I have an outer radius from x equals 0 out to x equals 2, minus my inner radius, which is just from an x value of 0 to an x value of x, so that's just x. But since I want to integrate with respect to y, I solve this equation for x and plug it in. So really this would have been x squared, but it becomes rad y over 2 squared. So that was washers. Now if I'm going around the x-axis, notice my region is flush against my axis of rotation, so this is disks. X-axis is horizontal, vertical rectangle, so that's going to be dx. X is going from 0 to 2. Put the pi out front. My radius is from a height of 0 to a height of y, so it would be y squared here, but y is 2x squared. So I plug in 2x squared for y. Now if I go around y equals 8, horizontal axis, so vertical rectangle. So once again, x is going from 0 to 2, pi out front. Now the outer radius is from the edge of the rectangle to the axis, that's a distance of 8. 8 minus 0 is 8, so 8 squared, minus the inner radius, which is a height y to a height of 8, so this is going to be 8 minus y, so it becomes 8 minus 2x squared, and you have to square that again, because again it's always pi r squared. And finally, going around x equals 2, no empty space here. This is disks, because again the area is right up against the axis of rotation. Vertical axis, so horizontal rectangle, that's a dy. Y is going from 0 to 8, pi out front, and this time this is a distance of x, this is a distance of 2, so this is 2 minus x. So it is simply 2 minus x, or 2 minus rad y over 2 squared. Here's another example of washers that's just has functions represented a little differently. It's a little bit more generic, you might say. We're taking y equals 0.5x plus 1, which is this line here. X equals negative y squared plus 3, which is this parabola opening left over here. So here's the region, and we're going to rotate it around x equals 5. So we're taking this region in here, rotating around x equals 5, and you can see we'll have a horizontal axis of rotation, so that'll be a dy. We need to find these y values. So to find where these intersect, we've got to set these functions equal to each other. So what I did was I solved this one for x. When I set them equal to each other, I can end up getting these two values, which I'll just call a and b. So my y goes from an a up to a b. I've got a pi out front. My outer radius is from 5 back to this x value. So this x value is 2 times y minus 1. So 5 times 2y minus 2 squared. My inner radius is from, again, the axis of rotation back to this part of the rectangle, the inner radius, so 5 minus this x value. So that's 5 minus negative y squared plus 3, and all of that squared. One more thing I want to point out, which can be a little tricky, and we saw it in that problem I showed where we went on 4 different axes, is let's say we just take this region, y equals x squared, x equals 2, and y equals 0. So this sort of triangular parabolic piece. Rotate around x equals 2. If we go around x equals 2, this is disks because the area is right up against the axis. So it's a dy, and it's disk, so there's my dy, there's my pi. Y is going from 0 up to 4, because 2 squared is 4, and this is a distance of x, this is a distance of 2, so this will be 2 minus x, and so this radius is 2 minus x and you square it. Now if we were going around x equals 0, all the drawing looks the same, except x equals 0, there's all this empty space, so this will be washers. It's still a horizontal rectangle, dy, so still pi and 0 to 4. But now because it's washers, I've got my outer radius, which is from axis to edge of the rectangle, so that's 2, so 2 squared, minus the inner radius, x equals 0 to x equals x, so that's x squared. So notice how these look very similar, 2 minus x quantity squared and 2 squared minus x squared, but they definitely represent different physical situations.